Just short introduction first. Dear colleagues, dear friends, it's my great pleasure to introduce our today's speaker, Alex Levchenko from the University of Wisconsin-Madison. He is tightly connected to Kharkiv. He graduated from Karazi National University in 2002, worked in the Usikov Institute of Radio Physics and Electronics. Since 2006, he's working in United States. He obtained his PhD in 2009 from the University of Minnesota. Then also worked in University of California, Argonne National Lab, Michigan State University, also shortly in Karlsruhe. And since 2014, approximately, he is working as a professor at the University of Wisconsin-Madison. In the theory group, condensed matter theory group. And today's talk is devoted to superconducting diode effects. Please, Alex, the floor is yours.
Yeah, thank you so much. It is very good to see all of the good friends and teachers. So thank you so much for having me. So yes, I prepared slides about relatively new topic, but it is all often the case that all new is well forgotten old. So at the end, I prepared some slides to show you a prehistory of the subject that goes back to 60s actually, but some renewed interest to this specific physics is in light of new materials and new physics that emerge in them. So most of the things that I prepared for you can be found in this review article that we wrote recently with my postdoc. So it contains both kind of pedagogical introduction to the subject, historical introduction, and many of the recent developments in the field. Okay, so first let me give you just an operational definition of what I will call superconducting diode effect, or very closely related to it, Josephson diode effect. So this is, in essence, the same phenomenon, but realized either in a bulk of a superconductor or in Josephson junction. So suppose that we would look at the current voltage characteristic of a superconductor under the current biased condition. So we will inject the current into the device and look at the voltage. So if the current is smaller than the critical current, we will be in the superconducting branch without the voltage drop across the contacts. And this will persist up until some critical value above which a system would jump into the resistive state. And so this jump is usually occurs at some critical value. The jump itself is not deterministic. There is actually a histogram of current switching distributions at which the current transitions to the resistive branch. This specific nuance that there are some histogram and there is some stochasticity in the switching is not so crucially important. For me, I will define this current at the mean field level. So I will calculate it from thermodynamics. I will show you just in a second how we will do this. But the key is that if we reverse the direction of the bias, the switching to the resistive state on the other branch of the IV curve would occur at the different magnitude of the current. And so this will signify this diadicity, meaning or non-reciprocity, so that the critical current in one direction is not the same as the critical current in the other direction. Okay. People also discuss non-reciprocity of the retrapping current. So if we decrease the current back, we would jump again into the superconducting branch again, and this retrapping in each of the directions would occur at different magnitudes. Okay, so this I will call a superconducting diode effect, meaning the effect that occurs in the bulk of a superconductor. A similar phenomenon can occur in the Josephson junction. This is magnified by the asymmetry in the maximal critical current of a Josephson junction in different bias directions. So if I would plot right now for the Josephson junction, let's say SNS type current phase relation, when current oscillates with the phase bias across the junction, then the magnitude of the critical current in one direction is different from the respective critical current in the other direction. So this would be the same physics, but realized in the Josephson junction device. So quantity of interest that signifies the strength of this effect is called so-called the Diode efficiency coefficient, which is a difference by the critical currents divided by their sum. So meaning that it would take current in one direction minus the absolute value of the current in other direction and divided by their sum. So the perfect diode would be when this efficiency is 1, and the good diode would be when this efficiency as close to 1 as possible. Okay, so these are just definitions. So there are many critical currents in superconductors. I will focus my discussion on a particular critical current, which we call a depairing current. So it's a thermodynamic quantity of a superconductor. I would like just to remind you the definition of the depairing current is given in the textbooks, and then we'll go from there. And again, for simplicity of this presentation, I will constrain myself to the discussion of the superconducting state close to the critical current, where we can use Ginzburg-Landau phenomenology. But of course, discussions of diode effects is not limited to proximity to critical temperature. We can discuss it at any temperature below TC, but details get a bit more complex, but the essence is the same. So I will use GL for its simplicity. You will see that even that would be quite complicated. So okay, so let's remind ourselves how we calculate the critical current in the bulk of a superconductor. So in the GL region, we expand free energy in the powers of the order parameter. We have quadratic term, we have quartic term, and then we have a term which is due to the condensate. So inhomogeneity of the condensate. So in Tinkham book, this term is presented as just the kinetic energy of the superflow. So he writes it as mass times the superflow velocity squared over 2. For me, it will be a little bit more convenient to talk about the inhomogeneous order parameter. So I'll write psi as spatially modulated with some collective Cooper pair momentum, which is captured by this exponential factor. So for me, Q would be related to the kinetic energy of the condensate. So we extremize or minimize the free energy with respect to the order parameter for a given value of Q. Okay, so this gives us an order parameter, and then from this free energy, by taking the variational derivative with respect to the vector potential, we can get a current, and we can calculate this current at this order parameter, which is in itself as a function of the collective Cooper pair momentum Q. So this function happens to be a cubic line. It has a maximum. And so by extremizing now current versus the Cooper pair momentum, we can get the profile of the free energy, which is this blue curve. This is the free energy gain of a condensate. So at 0 Q, this is the total condensation energy. But then there is a critical value of the Q where this gain is lost, meaning that we just gain too much of a kinetic energy. And this signifies to transition to a normal state. So at this value, we can calculate this critical current. So in this literature, it's called the depairing critical current. So at the GL region, it scales as a function of T minus Tc with a particular mean field critical exponent, which is 3/2. Okay. All right. So going to next slide. So I will discuss today in theory 3 critical works that are essential to understanding the non-reciprocity or this of this depairing current. These works are from Geschkenbein and Larkin from 86. One of the first predictions of the diode effect by Edelstein in 96, and very important work by Daniel Achterberg from 2010. Which was overlooked for many years, but it's sort of also conceptually very, very important. So this Dates are highlighted by red on this timeline. But this chart is actually a generated histogram of publications on this topic, which generated by keywords of current on reciprocity, diode effects, and superconductors all together. And actually, publications about this topic go back to 60s. They have been forgotten, I think, and right now some of this works has been revised more carefully. So in recent years, the boost to this interest to this effect was generated primarily by this article, which goes by the title "Observation of Superconducting Diode Effect in this niobium-based heterostructure." The plot on the right shows critical current as a function of magnetic field for different directions of the superflow. So the green line and this magenta line are different biasing directions. So if I would take a cut at the constant magnetic field, you see that there is a small difference of about few percent in the magnitude of this critical current between the green and magenta lines. And this difference becomes progressively smaller at the higher fields. So this signifies this diodicity that the critical current is not the same in different directions of this material. It is important that in this case, the magnetic field is in the plane of the device. It's not a perpendicular field. It's an in-plane field applied to this heterostructure. And I will talk about specifics of the configurations of the fields just in a little bit. So this experiment sparked a lot of interest. In just 2 years or 2 to 3 years after this experiment, many other experiments followed, and the influx of papers on the topic was enormous. So the people started writing review articles already few years into the studies of all of this physics. So the timeline of recent development of this first observation in 2020, about 2022. Further studies of diode effects and understanding the requirements for observation of this diodicity, primarily related to breaking of inversion symmetry and breaking of time reversal symmetry. So these are two essential ingredients that must be satisfied to observe these effects. And then how exactly you break them, either by fields or spontaneously in a system by interactions and so on, give rise to a very different possibilities how this phenomena can be realized. All right, so I would like to talk first about what is believed to be a first prediction of diode effect from Victor Edelstein and from 1995. So he published the paper which goes by the name of Ginzburg-Landau equation in superconductors with the polar symmetry. He was thinking about a three-dimensional system. And right in the abstract to the paper, he says that in this, he discusses a particular microscopic model that I will introduce to you to the next slide. But he makes a prediction that the Ginzburg-Landau free energy acquires a new term. And this term has a particular structure, vector structure. So it has a cross product of a unit vector along the polar axis. So this is C vector, crossed with magnetic field and dotted with the supercurrent. As you can see, this psi complex conjugated pi psi up to an overall factor is a superflow. So essentially, you have a new invariant, which is a vector product of two vectors and dotted with the third vector. And then he predicted that because of the existence of this new term in the free energy, and because it contains this covariant derivative, it also modifies the current. And as such, it gives rise to additional contribution to the current, which is field dependent. And as you can see, it's odd. Either changing the direction of the B field, which changed the magnitude of the critical current, or reversing direction of the current itself. So J would also reverse direction of the current. So in this formula here, F3 is some dimensionless function, which is not so much important. Delta is the ratio of the strength of the spin orbit coupling to the Fermi velocity. Hc2 is upper critical field. Psi is superconducting coherence length. So this was believed to be a first prediction. Somehow is what not noticed so much up until recently, I would say, but it was there for a very long time. I will come back to this formula many times because in the way that Edelstein predicted it, this particular expression is incorrect for subtle reasons that were not fully understood up until 2010, as I mentioned through this paper by Daniel Achterberg. And I will explain what kind of mistake was made and what was missed in this original prediction. So now let me introduce the model that I will discuss today that has these minimal ingredients necessary for us to discuss this diode effect in a superconducting state. So I would like to consider a two-dimensional electron system. I will include the following features. I would like to consider Rashba-type spin-orbit coupling in this system. And we will place this system in the in-plane magnetic field. So Rashba would split two parabolic bands, and the Zeeman field will also shift the respective parabolic dispersions. So this is represented, so one parabola, so the circle is a cut at a given Fermi energy, and the shift of the respective centers of the Fermi surfaces is governed by the in-plane magnetic field. And then on top of that, we would add just the usual BCS pairing, intraband pairing for this system. So these are three minimal prerequisites that gives rise to a diode effect. So this is more or less the model that Edelstein considered, although he considered a three-dimensional system rather than two-dimensional. And so he used the usual diagrammatics to derive Ginzburg-Landau free energy, and he derived this term. So I should say that in the literature, terms like that are called Lifshitz invariants. So the origin historically of this invariance comes from the studies of the second order phase transitions in volume 5 of Landau-Lifshitz. They are discussed extensively, and Lifshitz was interested in understanding under which point group symmetries you could write a particular invariant terms that contain linear gradient terms. As you can see, this invariant contains only linear gradients. So in order to write them down, again, you need to break some symmetries, and so primarily you need to consider point groups with broken inversion symmetries. So this historically how they've been considered in the context of the phase transition, but they arise generically, not only in the context of superconductivity, but actually everywhere. So let's say in magnetism, Dzelashinsky-Maria type interaction is an example of the Lifshitz invariant. So it contains this D vector, which is dotted with M cross grad M. They appear in liquid crystals, in flexoelectrics, in superconductors, and so on. In the context of phase transitions, the existence of the Lifshitz invariant results in the specially inhomogeneous order parameters. So we will be talking about cycloids, skyrmions, helical structures, and so on. So that's their physical manifestations. So in superconducting case, they give a helical state of a superconductor, and so this helical state also gives rise to a diode effect. For different point groups, they can be classified. So right now, let's say in a Bilbao server, for all of the point groups, you could essentially type whichever crystal structure you have, and you can ask a computer to generate you all possible Lifshitz invariants that are allowed in a given symmetry group. So right now it's completely optimized, so you don't need to even calculate them. They are given to you. So two historical notes. I didn't know about this, but I sort of learned about this by working on this topic and writing this review article. So I thought, and everybody thought, that Edelstein made the initial prediction, but reading this paper from Gorbatsevich with the title that has nothing to do with superconductivity, he considered magnetic properties of orbital antiferromagnets. It turns out that in section 5 of this article, he actually discussed superconducting state, which coexists with magnetism. And he actually points out that in these systems, there are Lifshitz invariants of a particular structure. And as you can see, he writes a term which is identical to what Edelstein wrote, but in a different system. And later in the paper, he also comments that if you put this material in a squid and subject to a magnetic field, you will see that fluxoid quantization will have an unusual phase shift. And this phase shift is related to this additional phase accumulated due to the existence of the toroidal moment. And in this particular discussion, but uh, um, that's also a manifestation of essentially a diode-like features. And he talks about additional contribution to a critical current due to the existence of this magnetization. Further, so this is 1988, just a word of credit to additional contribution. But then there is also another work from Levitov, Nazarov, and Eliashberg in 1985. They studied magnetostatic properties of superconductors without inversion center. At the very end of the paper, they make two predictions as a summary to the paper. And one of the predictions is the following, that first, the effect, the critical current flowing in one direction in a fine superconducting wire along the axis of which the magnetic field is applied is different from the current flowing in opposite direction if the material of the superconductor is characterized by the non-vanishing pseudo-vector beta. And the origin of this pseudo-vector is the same as I just explained. Again, it's a system with broken inversion symmetry. So they do not elaborate on the details, but sort of makes the prediction in writing that this should in principle occur. All right, so let me explain to you right now what was the mistake in the original work by Edelstein. It's very, very subtle mistake, and it was pointed out in this work about the magnetoelectric effects and FFLO, so fluidiferral Levchenko phases in superconducting materials. So Daniel Achterberg starts with the same description as the Edelstein. He writes the free energy. It's slightly different notations. I'm sorry, I took it from his article. So eta here represents the superconducting order parameter, and this particular combination, which contains linear gradients, is this Lifshitz invariant terms that we discussed with you that Edelstein derived in his work. So Daniel proceeds through a textbook order. He takes variation of this free energy with respect to order parameter. It gives you first GL equation, and this is this equation in the box. And this equation acquires a new contribution due to this Lifshitz invariant terms naturally. And then taking the variational derivative with respect to the vector potential give you a current. And the current can be written also as a Maxwell equation when J is just the curl of field, but here we also need to account for additional contribution, which is this magnetization part. And magnetization part comes from the fact that in superconductors, which breaks inversion symmetry, passing a supercurrent leads to a finite magnetization. So this is manifestation of the magnetoelectric effect in the superconducting state. So this effect itself also was predicted by Edelstein about the same year. All right, so with this equation, then Daniel makes an observation, and he says, well, you see, if we take right now an order parameter, and then we just make a gauge transformation. So we take another order parameter, which is just modulated by this exponential factor, which is was a properly defined collective Cooper pair momentum Q. And this Q is directly related to this Lifshitz invariant terms. It contains a particular combination of a field in this matrix K that multiplies this invariant term. Then he proceeds to show that this new term that exists in the current cancels identically, and it kills the diode effect. And he notes in his paper that this phase factor introduces above cancels exactly additional current contribution from the Lifshitz invariant. And then he writes a new free energy, which is which takes a manifestly usual form, where this Lifshitz invariant is simply not present. And it's very natural that any linear gradient can be simply gauged away, right? So it shouldn't change physics of a bulk of a material, and that's basically his argument. I will try to explain it in a very simple form. going back to the textbooks and the computation that we did with you on the opening slide. So if I start with the Ginzburg-Landau in the usual form, so we have psi4, psi square, and the quadratic energy part. In the Fourier components, the Lifshitz invariant that we wrote will have a quadratic in order parameter, but linear in Q contribution. And this term can be reabsorbed into the quadratic part of the free energy. Okay, I just can reabsorb it because it's quadratic. All it does, it simply shifts the free energy profile to a particular new minimum, which is realized at this collective Cooper pair momentum Q naught in the helical wave vector. But it doesn't change the critical values at which the gain of the free energy changes. Okay, so for this reason, the whole form of the shape remains the same. It just shift of the position of the minimum. And so in his article, Daniel concludes in his point 3 saying that the critical current in wires will show no unusual asymmetry, and this conclusion differs from the predictions made in reference 4. And reference 4 is a paper by Edelstein that we presented. So in 2010, he sort of unpredicted the diode effect, at least in its initial form. So I would like to connect this to a Josephson diodes as well and use this intuition between two effects to sort of understand what is really going on. So let's understand the same from slightly different perspective. Imagine right now that we have a junction of two superconductors. So I will have two order parameters, psi left, psi right, and I will couple them together. And there are different kinds of coupling terms that we can write. So usually in free energy of the Josephson junction, we write this cosine term, which is possible. But we can also write a sine term, which is odd in the free energy. It's only possible when we break time reversal symmetry. So the existence of these odd terms also has a long history. And the existence of these terms leads to a shift of a current phase relationship of a Josephson junction. It remains symmetric, but the minimum occurred at a different point. And it turns out that in the context of the Josephson effect, it has a special name. It goes by the name of anomalous Josephson effect. Okay, so it means that when you have a current phase relationship with this anomalous phase shift, and this phi naught is a non-vanishing quantity. So it was predicted originally, I think, in the work of Geschkenbein and Larkin in '86, where they discussed magnetic phases of heavy fermion superconductors, and they pointed out about the possibility of having this term. So linear combination of cosine and sine can be written as just a sine function with the modified critical current and the phase shift, which is the arctangent of the ratio of I1 and I2, these prefactors between two trigonometric functions. So of course, for a generic junction, which is not only a tunnel junction, we can write not only first harmonics, but any harmonic. And so generic current phase relation of a Josephson junction contains all cosines and all sines with the different current amplitudes, which depends on the particular harmonic. So this was kind of pointed out by Sasha Buzdin later on in Josephson junctions. And so all of these devices go by the name of anomalous Josephson junctions with a current of fixed current phase shift. So let us try to combine these two pictures together, meaning that the model that I discussed in the context of the Edelstein paper and this anomalous Josephson effect going towards trying to understand the Josephson diodes. So imagine that we will consider a Josephson junction of a type of superconductor, normal metal superconductor, but this normal metal will be a 2D electron system, so let's say 2DAC, with Rashba spin orbit coupling and magnetic field applied in plane of the junction. And so direction of the magnetic field can take some particular angle with respect to the boundary of the device. So we can solve this either through GL or through microscopic Garkov equations and so on in order to calculate the current in this geometry. and you will discover precisely this anomalous Josephson effect. So you will see that there is some critical current that depends on the Q vector. So this Q vector has a particular form, which is a unit vector n out of plane. So this would be analog of the C vector in the Edelstein notations. So in Edelstein case, because he looked at the 3D situation, the C vector was along the polar axis. In our case, the C vector is just a unit vector which is out of plane. And this unit vector is crossed with the magnetic field. So this is a particular structure of this Lifshitz invariant that we discussed with you earlier. And of course, because it's a vector in 2D, it has components which is along the axis of the junction and perpendicular to it. And so this vectors does two things. It modifies the critical current amplitude, and it also leads to a phase shift of a current phase relationship. So it turns out that in the simplest form, the existence of the Lifshitz invariant in its form derived by Edelstein in a simple case, when you retain only the linear gradient, does not give you a diode effect, but it does give you an anomalous Josephson effect with this phase shift. It also gives you a quite peculiar manifestations of the Fraunhofer pattern effect. So Fraunhofer is there, as you remember, are oscillations of the critical current when we apply magnetic field perpendicular to the device. So we need to exert a flux through the junction area. In this case, we do not do that. Our field configuration is opposite to the usual Fraunhofer configuration. So in this case, magnetic field is in the planes of the device rather than perpendicular, but yet the critical current will still be oscillatory with the strength of the magnetic field. All right, so this is that. So, I mean, this can be done in different junction configurations. I will skip that. So now how we can get, now if it's not enough to get the diode, how we can get it? It was observed after all. So it turns out that if you combine right now two features, the fact that you have this anomalous phase shifts and the fact that your current phase relationship has higher number of harmonics, these two ingredients together is enough to make a completely skewed current phase relationship. And this is generically present in any junction. Of course, we're not limited only to the first harmonic of the Josephson current. We'll have a second harmonic, will be already sufficient to generate the symmetry between the critical current in two directions. Okay, so this is how it's realized in Josephson junctions. But in the bulk of a superconductors, it also become clear what we need to do. So this linear Lifshitz invariant is, loosely speaking, analogous to a first harmonic in the context of the Josephson effect. But when we do a gradient expansion of the microscopic equations, we don't have to stop at the linear gradient terms. We can retain higher gradients in the expansion of the free energy. So let's say cubic term in Q, collective Cooper pair momentum would be third order gradient in real space and so on and so forth. And you can retain them to any order you need. So this was realized by several researchers. And so what was suggested as a resolution to this problem of original prediction by Edelstein is the following, that we need to write GL expansion like we normally do, retaining quadratic and quartic terms, but we need to be much more careful about the behavior of quadratic prefactor, this alpha coefficient, and quartic coefficient, beta coefficient, as a function of the Cooper pair momentum. So we have to work harder in order to capture this non-reciprocity of the critical current, at least in the Rashba model case. So despite this realization by several authors, people calculated this diode coefficient by using different methods and several papers that appeared relatively recently. So I collected 4 of them, which are very representative examples. And these calculations for exactly the same model resulted in different results, different predictions. So this first paper by Yuan and Fu, they used a BDG, so Bogolyubov-Dejen approach to do a computation. The group from Japan used a combination of, they kind of used a phenomenological approach similar to like a GL fashion. So another group from Japan used a kind of more numerical approach. So this group from Spain used a semi-classical Eilenberg equation approach to calculate this diode efficient. So all of them gave different predictions for what the diode effect would look like, and specifically they calculated this diode efficiency that I introduced for you at the first slide, and everybody got a different result. So it was a little bit discouraging, I would say. And I would say the most stunning statement was this statement from the Spanish group saying that even if you work really, really hard and very accurately account for this higher order Lifshitz invariant, at least in the GL region, the diode coefficient is 0. So they predicted that within the Ginzburg-Landau description of the Rashba model of 2DAC with BCS pairing, in this model there shouldn't be a diode coefficient, and so this kind of really contradicted to everybody else. It just happened that I was working with my student on this computation for this model as well, and we had yet a different result. So I'll try to convince you what I hope that our result is correct. I will try to reconcile discrepancies between these four works, and will tell you what I think is really going on. So we took a long time to calculate this coefficient. So this is only one technical slide that I would like to show that we actually have done the work. It's a very tedious computation in this case. And we calculated all of these Lifshitz invariants to a very high order in order to capture this effect in this model. This model has the following energy scale. So little h would be a strength of the Zeeman field. Alpha Rashba times P Fermi would be the energy scale of the spin orbit splitting. And then we also have, of course, the Fermi energy. So I would like to work in the hierarchy of energy scales when Zeeman field is smallest. Then we have a scale of Rashba splitting, and of course, both of them are much smaller than Fermi energy. And then we have an additional parameter, which is the strength of Rashba to Fermi energy. It's also a small parameter in the problem. And we have a final parameter, which is the Rashba splitting in units of TC. So this parameter is not fixed. It can be either large or small. And I would like to keep it as a parameter in the model. We calculate it at arbitrary value of kappa. Okay, that would be very important right now to reconcile with these previous works. So I would like maybe to go back for a second. Can I do that? Yes. So you see, all of these predictions contain these coefficients, alpha, beta, and so on. So alpha and beta are coefficients near quadratic term in the free energy and quartic term, and every coefficient itself is an expansion in the Cooper pair momentum. So a lower index 1, 2, 3, 4, and so on tells you to which order in Q you go. So let's say this paper predicts that the diode efficiency should scale as alpha 3. So they say that linear Lifshitz invariant is not enough, but cubic is already enough. So the group from Japan says, well, it's not only the alpha coefficient, but some beta coefficients as well, and so on. And it's indeed true that there is a very delicate interplay between all of these coefficients, and you need to be very consistent which ones you keep. So we kept them all, and this is the result that we got for this diode efficiency. So this diode efficiency is a non-trivial function of this parameter of the model, which is this spin orbit splitting in units of TC. We observe that it vanishes cubically with Rashba spin orbit at small spin orbits. So this again invalidates the prediction of Edelstein that is linear in spin orbit. This is not the case through this argument of gauge transform by Achterberg. You need to work harder. But it also vanishes at the limit of very strong spin orbit. So basically, if you have two bands that are very far away from each other, this effect is also gone because in our understanding, the non-reciprocity of the critical current, the diode effect, is interference of interband pairing in these models. And miraculously, or quite curiously, this prediction by a group of Spain that diode efficient vanishes in the limit that they calculate is actually correct, because they worked in the limit in our notations when this parameter kappa is very large. So what they observed, this vanishing diode coefficient, is a true statement of absence of this interference in the particular limit. They just choose sort of an unfortunate limited case. They work literally in kappa to infinity case of very, very strong Rashba spin orbit. So they observed vanishing effect, but in fact it's just very strongly suppressed, and we can calculate more precisely how it's suppressed in the limit of strong Rashba spin orbit splitting. Okay, so it's sort of reconciliation. Yes.
May I ask a question? And what about other predictions? Could you point on this diagram where the other three?
Yeah, so I would say that other three are just incorrect. They're inconsistent. So they didn't properly count for all of the coefficients in the free energy and then in the current. So as you remember, it's sort of a double, how to say, double extremization procedure. You first need to find consistently what your order parameter is at the given value of the Cooper pair momentum, and then you need to properly calculate the critical current for that value of psi. And all of these coefficients are entangled together, so you just could not simply throw out some coefficient somewhere and then calculate the current with some other coefficients. And so I would say that all of those computations, at least for this model, I would not make very generic statements for different models, but for this model, I think people just haven't been fully consistent how they calculate order parameter and current together. And the Rashba model happens to be extremely symmetric. It has too many symmetries, and I just don't have too much time to dwell on this. And this extra symmetries leads to extra cancellation. So it's a very small effect in the Rashba case. In actual numbers, this diodicity is like on the order of percent. It's very small effect. But in some other models, you can get a very, very sizable non-reciprocities going to 60, 80% in critical currents in different directions. Okay, so statement at least about these three papers that I mentioned, that Spain people are correct in the limit at which they did their calculation. So they calculated everything correctly. It just they choose an unfortunate limit to work, where this effect is vanishing in that limit. We can calculate the proper correction to it, and it's just small. The other three are correct conceptually what needs to be done, but contain some inconsistency in the way this computation is being actually performed. So that would be like a reconciliation. All right, so let me see. Okay, so this is like an essence of this very long story, that even this simple computation happened to be very controversial for a very long time. Some mistakes been made, and so some learning had to be done to correct for them. It was a long process. So this is how this critical current and diode coefficient should look like generically within the Ginzburg-Landau description. There are very complex functions of this anomalous Lifshitz invariant contributions, and then it's a job of a macroscopic model to calculate them specifically. So we calculated them in a variety of models right now. We looked at the effects of not only Rashba, but let's say Ising type of spin orbit. So Ising would be if you have, let's say, a two-valley system. Ising spin orbit would be just you can think of it as a local Zeeman field, which has opposite directions in opposite valleys. So we looked at the impact of simultaneously Ising type or Rashba type spin orbit coupling, and we see that as soon as you deviate from pure Rashba case, this very intricate cancellation effect is diminished, which leads to an increase of the diode coefficient. And we show here is that if you increase the strength of the Ising spin orbit, which is captured by this parameter kappa I, so the bigger value of kappa I, red line, as you can see, is a stronger diode coefficient, rising to about, let's say, 20% or higher in this model with the interplay of two effects. This has been measured in this niobium diselenite, niobium disulfide heterostructure, and they do see a results that I would say are quite consistent with the computation that we've done. We also looked at the effects of the disorder scattering. So any material is susceptible to impurities and imperfections. It is a much more difficult calculation to do, but we did it, and we also see a strong enhancement of this diode effect through an extrinsic effect. So extrinsic meaning it's generated by disorder. In this case, it leads to additional contribution due to the mixing of singlets and triplets in the superconducting state, which are promoted by disorder scattering. And this also leads to an enhancement of diode efficiencies. We also looked at some other mechanisms of diodes in superconducting interferometers under non-equilibrium conditions and so on and so forth. So up to this point, I'll probably skip these slides. Just want to tell you that this is an enormously big field. People are looking at different materials, topological materials, magnetic materials, and all kinds of exotic systems, and proposing different mechanisms how one can boost these diodes. Perhaps also with an idea to use them in actual superconducting devices as a useful switches that you could switch current in on and off by controlling either the voltage or gate voltage or magnetic field and so on. So the list of different contributions is almost endless. Right now, I could not even fit it in one slide. But as I said, we kind of surveyed all of the ideas that people had in our review articles, and so you're welcome to check. So I would like, at the concluding few minutes, just give a due diligence to people who actually saw it a very long time ago. So I spent some time digging through the literature, and I found results on this diodes and ratchets and so on going back to 60s. So I would like just to give you a couple of examples from the literature that I found. So one extrinsic effect that generate diodes are actually from vortices. So I found this work by Stewart and Hart from 1966, measurement of IV curves of superconductors in high field. And as you can see, their current voltage characteristics is diodic, meaning that the critical current in, let's say, negative direction is not the same as the critical current in upper direction. And they do comment in their abstract that they do see this in the critical fields in the range between the lower and upper critical field. So I would classify this as an extrinsic effect. It's not really a property of the material, but it's rather a property of the structure and generated vortex structure. So it's extrinsic mechanism of a superconducting diode. So there is another possibility which can occur in squids in interferometers. Actually, the simplest way to generate a diode would be to have a squid with two non-equivalent Josephson junctions that are characterized by two different critical currents. And then if you pierce it with the flux which is into the plane or out of the plane, then you will see a shift in the critical currents. And these shifts are shown by this histogram here, which plots the critical current amplitude versus magnetic field perpendicular to the junction area. And as you can see, by flipping the direction of the field, you shift them. And so this would be a manifestation of both anomalous Josephson effect and diode when you make sufficiently asymmetric junctions, the magnitudes of these currents will squeeze, and so they will be also skewed. And this experiment was done in 1967, first experiment of this type by these people back in the days. Okay. So this was also quite an interesting example of Josephson squids and fluxoids. So let's say it's possible to realize it even in a single elongated Josephson junction, as discussed in this article. So in this experiment, they discovered that by design of their device, they had a temperature gradient arising along the device. And in their interpretation, if you have a temperature gradient, then let's say in the hotter place, you have an order parameter which is smaller than the order parameter in the colder place. So effectively, due to the inhomogeneity induced by the temperature gradient, you also like effectively in a squid geometry, meaning that the current would flow unequally between the two, well, not two sides, but in the specially resolved configuration. So it will be also like a squid, and they also saw highly non-symmetric Fraunhofer pattern of this Josephson junction, which is also manifestation of the diode effectively. And more recent realization of diodes is done by a multi-terminal superconducting device. So let's say you have a three-terminal Josephson junction with a controlled gate. This is experiment recently done by the group of Gleb Finkelstein from Duke. And he showed that by the injecting the current, you could effectively switch completely the IV curve to one direction. So you have uh, a, a supercurrent that can flow only in one direction, just a one unidirectional superflow. It's a perfect diode, and this diode is actually field free. It can be realized in the device without any magnetic field. There is no contradiction here with this argument of broken time reversal and inversion because those ingredients are for thermodynamic currents. And here, dissipative current was used to control the junction state. And so out of equilibrium, you can create non-symmetry even without the use of external magnetic field. All right, so that brings me to a conclusion. So bulk of this work was done by graduate student who graduated and moved to the next stage of his career. So Joy have done some quite elaborate computations and learned all of this physics. We got enormous help from my postdoc, Daniel Schaffer, who participated in almost all of these computations as well. And in order not to make mistakes, we actually try to do these calculations in two different basis representations. So Joy was doing calculations in spin basis, and Daniel redone all of these calculations in helical basis, and we really spent almost a year trying to achieve a convergence between these two different methods. But we felt it need to be done not to repeat some of the mistakes and to get the consistent results. And then we've got a lot of help from Maxime from the symmetry analysis in doing joint work on this Rashba plus Ising case. And with Misha, we've done together work on this interferometers and Josephson diodes out of equilibrium. So I haven't had time to cover, of course, everything, but I hope that I gave you a flavor of this physics and the state of the field. And that's it. So I'm happy to take your questions. Thank you.
Thank you very much, Alex, for interesting talk and results. So we are now moving to questions and answers session. So please. So let me start perhaps with first I would like to ask about your general expression on the formula you obtained. So you still limit yourself in the series expansion by alpha 4 and beta 2 coefficients, or this is your general expression is valid?
So this expansion depends on a particular model. So how many terms you need to keep depends on a microscopic model that you consider. So we find that in order to describe the Rashba model that I presented to you, you need to work to a quartic order in the expansion in Q, both in the alpha term and in the beta term. And this final expression for this efficiency coefficient is a very, very complex mixture of all of those coefficients. And when you actually calculate these coefficients and plug them back into that formula, there is a tendency of mutual cancellations between these terms, as I said, because of some hidden symmetry of the Rashba model, additional symmetry, accidental symmetry of the model. If you consider other models that are not as symmetric, let's say you consider this additional case of Ising type spin orbit. You also, there is no such a severe cancellation anymore. And let's say having cubic coefficient becomes almost essentially effectively enough to have this diode. So the short answer is that in a case by case scenario, depending on the microscopics that is appropriate for your material or device, you need to check how many terms you need to retain to get the consistent answer.
Okay, thank you. And the second question I have is more for applications. So I'm thinking about the direction of quantum computing, how to then these superconducting diodes could be used in quantum computing schemes, circuits.
So I'm not sure about the quantum computation per se, but so of course people thought about the possibility using them as superconducting switches. So this has been demonstrated conceptually, meaning that of course you can switch on and off these currents or change their directions. I am, being honest with you, not sure about an attempt to use them in the meaningful way in a particular circuit for any kind of real application. I think that for qubits, it's probably not so useful because qubit operations require completely different setups and measurement schemes and so on. But perhaps for something uh, because they're intrinsically non-linear, the systems, so you could think about rectifiers and some other uses that are not necessarily for computing purposes, but maybe for some other electronics that use superconducting circuits.
Thank you. So Sergey has a question.
Yes, maybe it's a sort of continuation to what you asked, Andrei. I would like to ask about the numbers, how significant are those effects. But before that, let me ask you about spin orbit coupling. Well, we understood that for the for the superconducting diode effect, we need the Rashba spin orbit coupling, which is essentially a relativistic effect. We know more or less and understand that it is essential for two-dimensional electron gas for several reasons. How is it felt by superconductors? How it influences Cooper pairs? And can you give some numbers why it becomes essential, this spin orbit coupling?
Yeah, so in two DAGs, Rashba arises through invergent symmetry breaking at the interface. It can be quite a very strong effect, actually. So Rashba model itself is not super good for numbers, for big numbers of diode efficiency. It's the order of few percent. It's small effect. But admixture of different types of spin orbits, Ising type or some other types, or other materials where inversion symmetry has a more pronounced character can give rise to diodes that are very high. So you can get it at the level of 60% or 80% non-symmetry. So this effect can be quite strong. It's just the Rashba model, which was the first historically to be considered, happens to be a model where this effect is not as strong in terms of numbers. And again, let's say in a device that is operated, last example that I showed, you can effectively achieve a perfect diode. So let's say you can make such that current circulates only in one direction.
Thanks.
The next question is by Gleb Skorobogatyko, please.
Okay. My question is about this minimum of Josephson current at non-zero momentum of Kuiper pairs. So if to look on this from a bit different angle, does it mean that at non-zero momentum of Kuiper pairs, if you have a zero Josephson current, then it requires fine-tuned phase coherence in superconducting phase. And is this effect fragile with respect to fluctuation, for example, because this phase coherence is needed? So what
That's
can
right.
be?
So no, I think it's robust. I would say that the existence of this helicity. So basic statement is that even if you have a helical state, let's say a specially modulated order parameter, it doesn't carry the supercurrent in the ground state. That's a statement, and that's just a thermodynamic statement. It is not really a fragile state, but again, then breaking proper symmetries, applying the fields and creating junctions, then you could generate this currents out of the helical state.
Thank you. So we have the next question from Oleg Turutan. Please.
Thank you for your report. It's a very interesting topic and a naive question from a non-theoretician. In those intrinsic effects, can we speak in bulk superconductors?
Yes.
Could we speak about effective non-reciprocity of critical current density, different critical current density in those direction, or maybe of the density of superconducting carriers, charge carriers? Just as effective.
Yes, correct. Yes. It is possible. Yes, that's right.
And
So let's say in the presence. So we can relate superfluid density of states, but then again, if you break these symmetries as we discussed, both time reversal and inversion, then the coherence peaks in the density of states will be non-symmetric, and so this would translate to asymmetries in that regard.
if we measure experimentally those values, say the density of carriers by tunnel effect, tunnel microscope, or the velocity of those, will we see the difference?
Yes, you will, and it's been done in some materials, precisely even in tunneling. Yes.
Okay, and the second question: would the sense for looking those complicated intrinsic effects if there are also already from 60s very simple vortex generated?
Excellent. I would say that this is precisely the essence of the interest. People are interested in finding situations when you can remove all artificial stuff and study the pristine property of the given material that realizes. So I would say most of interest is not so much to generate it. There are all kinds of cheap ways to do it.
Not so practical meaning, but
but actual whether the given
basic
material intrinsically has this property. I would say this is the most interesting part.
Thank you. Thank you.
So I don't see other questions. If it's not the case, let's thank the speaker for nice and interesting discussion during this session. And thank you all for participation. With this, I would like to inform you that we have Christmas holidays, and we are looking forward to seeing you in January 2026. So wish you all happy holidays and happy new year then. Thank you.
Thank you for the invitation. Thank you for
Thank you, Sasha.
Thank you, people.
Thank you.
Goodbye. All the best.